This is going to be a quick video on how to calculate enthalpies of reaction. And if you don't really know what enthalpies of reaction are, I'm going to assume that if you're looking for this video, chances are you probably know what they are. But pretty much the whole idea is you're trying to see exactly how much energy a reaction is either going to absorb or release depending on the energy level of the products and the reactants. And so the entire point of all of this is really so that you can find your change in enthalpy of the reaction. Now, what we have in front of us here is the average bond energies for a lot of bonds. We're not really going to need a lot of them. They're all here on the table. Your decision as to whether you're going to need to get one or the other is entirely dependent on whatever your reactants and whatever your products are. And so in this case, we have HCN, or cyanic acid, reacting with 2 moles of hydrogen gas, going to give you something called methylamine, or CH3NH2. It just depends, whatever you want to call it. Doesn't really matter. The point is, this is what you have. And so, really what's going to happen is, schematically, you're going to take your reactants, you're going to rip them apart into their respective elements. So you're going to make a bunch of hydrogen, carbon, nitrogen. Those atoms are going to be separate. And then you're going to go ahead and turn them right back into the products. Now the thing is, when you go in this direction, so if you assume that you take all your reactants, you rip them apart into the respective elements, hydrogen, carbon, nitrogen, you're essentially going to be breaking the octets in the bonds that are holding the structures together, and that is going to take a lot of energy. So this is going to require energy. How much energy? Well, that energy is entirely dependent on whatever your reactants are. Now, when you take this step, and you decide to take those individual atoms and you try to make your product here, that is actually going to allow you to reform bonds in a slightly different way. But because you're reforming those stable octets, you're actually going to release energy because of it. So the entire goal of everything that you're going to be looking at is essentially to see how much energy your reactants have that you're going to need to put into the reaction to invest into it. And then once you form your products, you're going to see how much energy you release back, to see exactly how much of a return you're going to be getting on your energy investment. And that's honestly what it is in its most basic form. Now, the issue with that is because there are different ways to bond, we actually have no idea how much of each we have. For example, if you take something like the HCN, if you don't know general rules of how to form structure, you actually might not know if it's a carbon single bonded to a nitrogen, maybe it's a carbon double bonded to a nitrogen, maybe it's a carbon triple bonded to a nitrogen. You have to know the quality of each bond in order for you to know how much energy is going to be in that bond. Which means, unfortunately, you can't actually do this off of the formula. You actually need to know the structure of each one. So I'm going to draw these out right now. And what I'm going to do is I'm going to label them reactants and products respectively. That way I kind of keep the calculations separate. So we have the reactants, and in this case, when you look at the reactants, well, the reactants are always on the left side of the reaction. So you get HCN, which looks like this once you make the structure. And then you're also going to be making hydrogen gas, which looks like this. Now the thing about hydrogen gas is you're actually going to have 2 of them because, again, your coefficient tells you have 2 molecules of that. So in reality, we need to consider the fact that we're probably going to need to break both molecules apart. Okay, well, if we're going to do the calculations on this, well, one of the things I like to do when I'm calculating bond energies, especially when you're first starting out, is I like to circle the bonds that I'm going to be working. So here I see a carbon triple bonded to a nitrogen. I would go on the table, I would find it, and I would see it here. And I'm circling it in blue so you can follow along. That's so you can find it on the table. Carbon triple bonded to a nitrogen. And then at the same time, I also notice that I have a hydrogen bonded to a carbon, a single bond. I would look at that up here on the table, and you see it right here, 413. And then finally, I have the 2 off to the side, hydrogen bonded to hydrogen, both of these. And again, you just simply look at the table and you see exactly how much energy is going to be within that bond. So now that you have this, all you have to do is pretty much add up all of the bond energies that you have in all of your reactants so that you know exactly how much energy you need to put into your reaction to break everything apart into their respective atoms. And so in this case, for example, if we take the red to signify how much energy is in a carbon-hydrogen single bond, well, this would be 314 kilojoules per mole. You would look at how much you have for your carbon triple bond, and that one is going to be 891 kilojoules per mole. And then when you're going to be looking at your hydrogen, you need to realize that because you have 2 hydrogen, you need to take both of those into consideration. So it's actually going to be 4 times 436 kilojoules per mole. And then once you have this, assuming that you add everything up, you should get exactly how much energy your reactants have within their bonds. And in this case, what you're going to find is that your reactants actually have around 2,176 kilojoules per mole in terms of energy when it comes to the reaction. All right, cool. So pretty much, again, like I was saying, this is how much energy we need to put into the reactants to tear them apart. Now we need to see how much energy we're going to get back when we actually make the products, whatever it is that we're going to be making. So for this, we're obviously going to need to make sure that we do products. And in this case, we only really have one product. But regardless of that fact, we do need to look at the structure so that we know exactly what we're dealing with. Well, this structure is actually relatively simple. Methylamine, even though it's somewhat more complicated than what you saw above, is in general not really that much difficult of a structure. It just kind of looks like this. But we still want to make sure that we're going to be following along to check to see exactly how much of each one we need. And so we need to look at the quality of each bond. Now for these, I'm going to reset these so that we can actually bring them back. And when we look at this and we look over here, okay, well, first of all, I see that I have 1, 2, 3 carbon-hydrogen bonds. So if I'm thinking about the carbon-hydrogen bond, again, you would go up here. Carbon-hydrogen is 413. There's 3 of them, as you can see by the 3 circles. So that means I have to take all 3 into consideration. 413 kilojoules per mole. All right, so that's all the energy I have in all my carbon-hydrogen bonds. All right, well, what else do I have? Well, I have a carbon-nitrogen bond that I have to take into consideration. It's a single bond. So I would go up here to the table. I would see carbon-nitrogen bond. I see it's worth about 293 kilojoules per mole within that bond. And so that's what I would write. I would just add 293 kilojoules per mole because I only really have one type of that bond. And then finally, the other type of bond that we have is nitrogen-hydrogen, for which we have 2. And same idea. You go back up here. You check a nitrogen-hydrogen single bond, which we find over here on this side of the table. That's 391, but because we have 2, we have to take that into consideration. And so it's 2 times 391 kilojoules per mole. And then this is going to give us how much energy our reactants are going to release when they actually form according to the bonds that they're going to be creating. And you're going to find that you're going to be making around 2,314 kilojoules per mole. Okay. We now need to, the whole reason why you're doing these bond energies, you really should be focusing on trying to contextualize what it is that's actually happening here. So, in this case, if we look at this number up here, the 2,176, this is essentially energy in that we're going to be using to break. Energy in to break. That's the idea. When you look down here at the bottom, this energy is going to be energy out when you make. And let me give myself some more space. Okay. The best way to really understand this, if you want to just get the math on a concept basis, not even just memorizing and being like, oh hey, it's this formula, is to think about it in this way. We have about 2,176 that we need to put in. Now, when you look at standard enthalpy diagrams, what that means is that if you're thinking about how much you're going to put in, well, again, it's 2,176. So you can think about it as if, okay, well, here's my starting point in terms of energy. I'm going to put in 2,176 kilojoules per mole. If my handwriting would cooperate with me, I could actually show you that, but apparently it doesn't. Now, the problem is, on the return, how much you get out. Well, you're actually going to be returning a little bit more than what you actually started with. You return back with 2,314 kilojoules per mole. And so what that means then is that you actually end up being at a lower energy state because you released more energy than you actually put in. And in fact, when you're doing all of this stuff, if you really want to understand what change in enthalpy is, this difference from start point to end point is going to be your enthalpy. Which means if you really want to understand what that difference is, the entire idea would be to take the energy of your reactants and then subtract that from the energy of your products. And this is a general formula that we use so that we can actually calculate the enthalpy of a reaction. And so in our case, what that's going to be is that it's going to be 2,176 kilojoules per mole. You would subtract the energy of your products, which is going to be 2,314 kilojoules per mole. And then once you solve for that, which should be a relatively easy number, you will get what your reaction is going to give you out. Now, in this case, it's going to be about negative 138 kilojoules per mole. But that negative is very, very important, because if you look at this reaction, and I'm going to circle what I'm talking about, when you're doing any kind of enthalpy change, you only really need to worry about the start and the ending. You don't really care about the process or the path that you take to go from start to finish. All you got to do is worry about, where is my state at starting, where is my state at finishing, and that's all you need to know. And so in this case, when you solve for it and you get the negative 138 kilojoules per mole, that's implying that you released energy, because this energy that we see here off of this enthalpy was essentially released out. And so you can pretty much go ahead and say that this reaction is going to be exothermic because you release energy. It's like the same thing as saying that a ball is on this hill and it's going to roll down on the hill at the bottom, and when it does that, it's going to release energy. So at the end of the day, to recap, to make sure that you really understand what's going on, you're going to use a table and you're going to use the structures to figure out exactly how much bond energies there are. And then at the end of the day, really what you're going to do is that you're going to take the energy of your reactants, subtract the energy of the products, and then that will give you whatever your answer is. If it's negative, you can go ahead and call it exothermic. If it's positive, you can go ahead and call it endothermic.